So the partial derivatives that we looked at in the previous two videos would be analogous to like the first derivative with a single variable function. So we have two different first derivatives or first partial derivatives. But we can go further than that, just like we can with functions of a single variable. We can have the first derivative, the second derivative, the third derivative, etc. And we saw various applications of the different derivatives, mostly just the first and second, but we dipped into the third and fourth and stuff like that throughout Math Tools 2, right? Like when we had the Taylor series, we needed all of the derivatives at that point. We saw that the second derivative corresponds to acceleration in regards to like a position function, whereas the first derivative is velocity, right? So we saw various uses for it. So same idea with the second order partial derivatives, the second or just the second partial derivatives. They will also have various uses here. So let's look at an example function. So if we look at, I don't remember if we already used this one or if this is a new one, but let's look at 2x cubed minus 4xy squared plus 5y cubed minus 6xy plus 5x minus 4y plus 12. So pretty well-behaved function, right? It's going to be a continuous function. It's basically like a polynomial kind of function. Nothing really weird going on with like denominators or roots or anything like that. So the first partial derivatives, we typically call these the first order partial derivatives. Okay. And then the second ones we call the second order partial derivatives. So we already saw how we would do this, right? We would do the partial of f of with respect to x would be, in this case, we'd have 6x squared minus 8y. No, sorry, we're doing it with respect to x. So this would just be minus 4y squared because the 4y squared is the constant part. The x is the variable. Plus 0 minus 6y plus 5, 0 and 0. Okay, so this would be our answer here. Then if we did it with respect to y, we would get 0 minus 8xy plus 15y squared minus 6x plus 0 minus 4. Okay, so these are our two first order partial derivatives. So now if we go into the second order partial derivatives, first of all, how many are we going to have? Well, to take the second derivative, what we do is we differentiate the first derivative. But we have two different first derivatives, and we can differentiate both of those either with respect to x or with respect to y. So we can take our partial derivative with respect to x, and we can differentiate that with respect to x, and we can differentiate that with respect to y. And then same thing with the one with respect to y. So altogether, we're going to have 4 second order partial derivatives then. So let's go ahead and look at what those would be. So our first one, the notation we would use is either this. Okay, so just like the normal second derivative notation that we had, it's also commonly written like this. Okay, so this would be read as this is the first variable you take the derivative with respect to. This is the second one. So here we're taking the derivative with respect to x twice, basically. So we're going to take our partial derivative of x and then differentiate that with respect to x. So we're going to get 12x minus 0 plus 0. Okay, so we'll just get 12x here. So now if we take that same derivative, but then we differentiate with respect to y. Okay. So actually this is written backwards. Okay. So if we're going to take that one, so if we're going to take this one and differentiate with respect to y, then this is how we would write it, because this is read as the derivative with respect to y of the derivative with respect to x. So then the dy ends up on the left side. Okay. Now, it's not going to matter in a lot of cases, because what we're going to see in the next video is that oftentimes it doesn't actually matter which one you do first. So we could differentiate with respect to y and then x, or vice versa. And in a lot of cases, we're going to end up with the same thing, but not in every case. So, it'll matter for like those edge cases. Now in the f notation, it's backwards. Okay, where we just read left to right which variables we're taking the derivative with respect to. So here we're taking the derivative with respect to x and then y. Okay, so these two notations, the Leibniz notation and I don't remember if this notation has like a specific name, if I said it in the video or not, but in this notation, they are backwards. Okay. So let's go ahead and look at what that would be then. So this first term would just be 0. This term would be negative 8y. And then this term would be negative 6. And then the rest would be 0. Okay. So we get negative 8y minus 6. All right, so now let's look at the y term, the y partial derivative. So first we'll just take that one and we'll differentiate with respect to y again. Okay. So here we'll get negative 8x, okay, plus 30y, taking the derivative of this one, and then the rest is going to be 0. Okay, this one will be written as fyy. Now the other partial derivative, so dx dy. So by the way, we call these ones mixed partial derivatives because we're taking the derivative of two different variables. So the the variables are mixed. So that's why we call them mixed partial derivatives when we are doing two separate variables. So these ones, the y squared one and the x squared one, those would not be mixed partial derivatives. So as I said, in most cases, we should get the same thing. This is a relatively well-behaved, easy function in that it's like continuous and there's no issues with it. So in this case, we probably expect to get the same thing. So let's see what happens here. So we're going to take the derivative of this one with respect to x now. So we're going to get negative 8y, and then just minus 6. Okay. Which is indeed exactly what we got for the other mixed partial derivative. Okay. So this one will be written as fyx. So again, we're not going to get the same answer in every case. So in general, you don't want to assume it unless you know that it meets the conditions, which is what will be the focus of the next video. So let's just do another example here. So I have this function f of x y equals x e to the negative 3y plus sine 2x minus 5y. Haven't really looked at any, I don't know if we've used any trig example yet, so might as well just throw one in there. Again, we're not going to focus on trig, but it pops up every once in a while. But you don't need to worry about trig in like the quizzes or tests or anything like that. So I kind of prefer just using this notation here, personally, just because it's easier to write than having to write these looping D's all the time. But I think maybe when it's typed, I kind of see this one more. I don't know. I kind of see both of them a lot, so I'm not going to really say that one's more common than the other, but I kind of prefer this notation just because it's easier to write. Regardless, we should take the first partial derivatives first, just for a frame of reference for when we're taking the second partial derivatives. And by the way, you can do the same thing for the third partial derivatives, etc. You're just going to end up having a lot more. And we're typically most concerned with the first two sets of partial derivatives. The other ones don't come up as much in applications. So, we'll just focus on the first, on mostly the second partial derivatives. But if you think about like the third order partial derivatives, then you're going to have 4 derivatives that you can each differentiate each of them twice. So then you're going to have 8 total third order partial derivatives. So in general, you would have 2 to the n, where n is whatever order you are, nth order partial derivatives. Okay, but a lot of them are going to end up being the same because all the sets of mixed partial derivatives that are equivalent should end up being the same in most cases. But again, not in every case. So anyway, so this one, the first partial derivative with respect to x. So the e to the negative 3y is the constant part. Plus, remember the derivative of sine is cosine. We're going to need the chain rule here. Okay, so times the derivative of the inside, which is going to be 2. So I'll go ahead and throw that 2 up front. Okay, and then for y, we're going to get negative 3x e to the negative 3y, again using the chain rule. And then the chain rule will give us a negative 5 on the outside, so again I'll put that in front here. Okay, so hopefully we're comfortable just taking these, the regular derivatives at least. Okay, so again we're just treating the opposite variable as a constant. Okay, so now we want to go ahead and differentiate each of these with respect to both variables. So we'll do fxx first. Okay, so this part doesn't even have an x in it anymore, so that's just a constant at this point. Derivative of cosine is negative sine, so we're going to have negative 2 sine of 2x minus 5y times 2 again. Okay, and I'll go ahead and throw that out front again just to make this look a little nicer. So we're going to have negative 4 sine of 2x minus 5y. And then we'll do f of xy. So here, differentiating this with respect to y then. So we're going to have negative 3e to the negative 3y. Here, the chain rule will give us a negative 5 out front. So, and then the derivative of cosine is negative sine, so those two negatives will cancel, and this will be 5 times 2, so 10. So 10 sine of 2x minus 5y. Okay. We'll go ahead and do the other mixed partial derivative first, since, it should be the same as this one, so we'll just put them right next to each other here. So derivative of this with respect to x will indeed be negative 3e to the negative 3y. And then here, the chain rule will give us that 2. The cosine derivative will give us negative sine, so that'll cancel the negative out. So we're going to have plus 10 sine of 2x minus 5y. Okay. And then finally, we can do fyy. So here x is treated as a constant. So negative 3 times negative 3, so 9x e to the negative 3y. This will give us a negative 5, and then this will give us a negative when we differentiate. So overall, we're going to have a negative because we have 3 negatives. And then 5 times 5 will give us 25. So we'll have 25 sine of 2x minus 5y. Okay. So 9x e to the negative 3y minus 25 sine of 2x minus 5y. So we have 4 partial derivatives. The 2 mixed partial derivatives are equal in this case, as they will be in a lot of cases. But in general, we still consider this to be 4 second order partial derivatives.